Assalamualaikum, very good morning. For today's lecture, we're going to proceed with a lecture 19, in which the topics covered will be based on chapter 7, which is on the magnetic material and influence. So this is a continuation from lecture 18, which has been previously given to you. So for this lecture 19, we're going to start our discussion on magnetization. Okay, magnetization, and also on the effects of magnetization. So basically, this will be related to the magnetic material. Yeah, so that should be the first topic on magnetic material. And following that, we're going to have a look on the boundary conditions. Yeah, boundary conditions in magnetic material. So basically, there will be two main topics that will be covered in lecture 19. The first one is on material, related to magnetization and also the effects of this magnetization. And number two will be on the boundary conditions between two magnetic materials. So this will be the main coverage of lecture 19. Right. So let's have a look on the slides of lecture 19. Reference for this lecture 19, you can get it from Sadiku, page 372 to page 386. Right, so for the first part of lecture 19, we're going to proceed with the lectures on magnetic material, and the second part will be on boundary conditions. Yeah. Okay, so this will be the objective of lecture 19. We have four main objectives, in which the first three are related to the magnetic material, and the fourth one will be based on the second topics, which is on the boundary conditions. So let's have a look at the first three objectives related to the material discussion. We're going to have a look on understanding the concept of magnetic polarization. Yeah, so this will be the topics, the main things that we're going to discuss in this lecture 19, the first part, which is basically the effect of atomic orientation due to applied magnetic field. So that is what we meant by magnetic polarization. Yeah. And secondly, we're going to investigate on the bound magnetization current in a polarized material. So from the first objective, in which we are going to understand the concept of magnetic polarization, so this polarization will then give rise to this particular current, which is called as a bound magnetization current. So we're going to have a look on relationship between the magnetic polarization and also the produce bound magnetization current, which is produced in polarized material. And thirdly, we're going to investigate on the effect of magnetic polarization to the resultant magnetic field in material. So we're going to have a look, basically, we're going to find a relationship between the flux density B, yeah, and also the magnetic field intensity H. So we're going to have a look on what should be the direct relationship between the flux density B and the magnetic field intensity H in a magnetic material. So that should be the third objective for the first topic of lecture 19. Yeah, and for the fourth one, the fourth objective, this will be related to the second topics of lecture 19, which is to understand the concept of boundary condition between two magnetic materials. Okay, so let's start with the discussion on magnetic polarization. What is meant by magnetic polarization? So this is somehow similar to what we have seen before in dielectric material discussion in chapter 5. We have learned about the electric polarization, which is the effect on the dielectric when it is applied with the external field intensity, electrical field intensity, the E. Yeah. So somehow it's similar in terms of the concept, in which you're going to have a look on what should be the behavior in your magnetic material when we have externally applied magnetic field intensity. Okay, so we're going to have this material, which is said to be applied with external field. Yeah. And in this particular case, we assume that there is no external field applied. So this material is said to be in ideal condition, yeah, whereby we don't have any applied magnetic field. So we can discuss, or we can then say that the material can be, the view of material can be in two different views, where we can have it in terms of a microscopic views and also a microscopic view. So these are the common views that we're going to have a look related to this magnetic material. So we're going to start with the microscopic view here. Yeah, microscopic view down here, whereby we can see that this is what happens in one atom. Yeah, one atom of your magnetic material, whereby we can say that there should be a current that will be produced in your atomic structure in each atom, in which this particular current is said to be produced due to the electron movement. Okay, electron movement, because you know that for each atom, the electron will move in its orbit. So this movement of electron will then produce the current. Yeah, will produce the current. So basically, this current is current that is said to be bounded and produced in or generated in your atomic structure. And the resulted current here will then produce what we call as a magnetic dipole moment. Yeah, a small vector of m. So this small vector of m basically is a force. I can say is a force which is produced in one atom due to the production or due to the generated current in each atom. Okay, so this will be the microscopic view, the view of one atom of the magnetic material. And in terms of a macroscopic view, we can have here numbers of atoms or numbers of dipole moment which are said to be randomly oriented. Yeah, randomly oriented because there is no applied magnetic field. So these particular atoms or this particular dipole moment are said to be in their random orientation. So due to this random orientation, we can say that these dipole moment will be cancelled. Yeah, will be cancelled out. Yeah, the dipole moment will be cancelled out because the orientation of dipole moment are random. Okay, so from here, we can say that there should be two main observations that can be made when there is no applied field, there is no applied magnetic field to this material. The first one will be randomly orientation of your dipole moment. Yeah, randomly orientation of a dipole moment. That's the first one. And secondly, the total dipole moment, which is a summation of m, which is then written to be a a capital vectors of m. Yeah, capital vectors of vector m here, yeah, is known to be a magnetization vector. And due to the random orientation of your dipole moment, yeah, we can see that the summation or the total dipole moment in your magnetic material are said to be 0. So the magnetization vector for this particular case will then equals to 0. So the units for this magnetization vector is in ampere per meter. Yeah, so that should be your the first condition, the first observation when there is no applied magnetic field to your magnetic material. Yeah. Okay, now we're going to proceed with the second case whereby your material are said to be applied with external field. Yeah, so now we have a case whereby the B is not 0 anymore. Okay, the B is not 0 anymore. So we can say that in your macroscopic view conditions, yeah, we can see that your dipole moment will be aligned. Yeah, will be aligned according to the direction of your external field. Yeah, so we can see that all of these dipole moment are said to be aligned according to the direction of magnetic field, and as such, we can have two observations. The first one is dipole moment orientation is according to the magnetic field direction. This is what we call as a polarization. Is said to occur in your magnetic material because your dipole moment is aligned according to the direction of external field. And secondly, we can see that the value of magnetization vector, the capital vectors of m is not 0 anymore. So there is a value, there's a result for this capital vector of M, in which this capital vector of M is the summation of a small vector of M, the summation of the dipole moment in your magnetic material. Okay, so magnetic polarization is also known to be magnetization. Is occurred when there is applied magnetic field to your magnetic material. Yeah, right. Okay, so we have done with the first objective. So we have understand the generation of magnetization or magnetic polarization, which is produced when there is an external applied magnetic field intensity to your magnetic material. So we're now going to proceed with the second objective, which is on understanding the bound magnetization current. Okay, so again, we consider same materials here, the same materials, and there is applied magnetic field to this material. Okay, to this material we have B, which is not zero, which is applied magnetic field to this particular magnetic material. So we can have the effect whereby dipole moment will be aligned according to the direction of your magnetic field. Yeah, so this is your dipole moment, which is a small vector of M. So this is one dipole moment or equivalent to one atom. So we are going to have numbers of atoms, millions of atoms, billions of atoms in your material. So this will be the alignment of those dipole moment. So we can see that the alignment is given to be just in this particular sample. So for example, here we have one, two, three, and four samples of dipole moment or samples of atom which is aligned on this surface. Then for the top surface we have one, two, three samples, and so four samples of atom or four samples of dipole moment which are aligned on the top surface of this particular material. But in reality we have millions or billions of atoms or billions of dipole moment aligned in this particular structure. So we can then see that from this argument, I mean from this diagram, we can have that this particular dipole moment, yeah, will then produce a continuous current on this particular surface, on this particular top surface. Yeah, and also this dipole moment on this side will then produce a current on this particular surface. Yeah, so we can have this kind of current. Yeah, this kind of current which is produced on the surface of your material, but in reality this current is not free current. This is what we call as a bound current, because the current is produced by the atoms, and the atoms is strongly binded to the structure. Yeah, and that's why we call this particular current as a bound magnetization current. Yeah, so we can have two types of current related to this bound magnetization current, yeah, in which those current are, the first one is called as a bound magnetization surface current density, in which this particular current is located on the surface of your material, yeah, on the surface of your material, which is denoted to be having a symbol of JSM, a vector of JSM, SM stands for the bound magnetization surface current density, and it is related to the magnetization vector M from the equations of M vector cross product with a normal linear vector. Yeah, M vector cross product with normal linear vector. For instance, yeah, for instance, if we have vectors of Z in this direction, a vector of Y in this, sorry, X in this direction, and vector of Y in this direction. So we can say that for this particular surface on the top, yeah, on the top here, we can see that the normal linear vector for that surface will be in the Z direction. So for this particular surface, the current of JSM produced in this particular surface will be given by the M vector, or the magnetization vector, cross product with the normal linear vector for that surface, which is Z direction. And similarly, for this particular surface, yeah, on this side, we can see that the normal linear vector from that surface will be in the X direction. Yeah, so the JSM on this surface will then given by M vector cross product with normal linear vector, which is X direction. So that should be your a bound surface magnetization current density related to the surface vectors for each particular surface. Yeah. All right. And remember that the units for the JSM is ampere per meter because we are dealing with surface current. Yeah. And the second type of bound current is what we call as bound magnetization current density, which is produced in your material, inside the material. And this Gm or the symbol for this bound current density is given to be Gm vector and is given by the curl of the M vector. Yeah, the curl of the M vector. And the units is ampere per meter squared because this is a volume current density. Yeah, so Gm basically is a volume current density and JSM is a surface current density. So that's why we have different units for JSM and the Gm. Yeah, so JSM is a surface current density. Jm is a volume current density which is produced inside the material and is given by the curl of the M vector. So depending on your problems, you need to consider the use of appropriate curl operators, depending whether the problem is related to the Cartesian, cylindrical, or spherical systems of coordinate. Okay, so we have discussed about the curl operators in our previous discussion on lecture 17. Yes. Okay, so let's have a look on the first example related to the concept of magnetization and bound magnetization current. Okay, so the first examples here, we are given a long cylindrical structure. Yeah, a long cylindrical structure with a magnetic material of radius A is found along the z-axis when the magnetization vectors M is equals to 10 of Z in ampere per meter within the cylinder. Find the first one, find the Jm, and secondly, find the JSM at R equals to A on the magnetic material surface. Okay, so basically this is related to the concept of bound current. Yeah, and we're going to use the equations for the bound current, which is related to the magnetization vector of M. Yeah. Okay then. So let's have a look on the first one, which is cylindrical structure. So we have, this is your cylinder. Okay, cylinder, long cylinder. We're not given any information about the length. We have a radius of A for the cylinder. Then it's given that the magnetization, the M vector, which is directed towards the 10, towards the Z-axis. So we have M of 10 of Z. So we need to find the Jm. Okay, we need to find the Jm. So Jm, which is the volume current density inside the material, should be given by the curl of M vectors. Okay, and for this, we need to relate to the cylindrical system because we are dealing with the cylindrical system. So we need to check the curl equations for the cylindrical systems. Yeah. Okay. So from here, we know that the M is in a Z direction. So basically, from the equations of curl for spherical system, we can write that the curl of M should be given by 1 over R dmz minus d phi over d phi, sorry, dmz over d phi. This is the Z component of the M vectors, yeah? Minus, okay, dm phi over the dz. Right, this will be in the R direction, okay, plus dmr over the dz minus dmz over the dr, which is in the phi direction, plus 1 over r, okay, d over dr, sorry, dr m phi dr minus dmr d phi in the z direction. Okay, so this will be the curl of the vector of m in the cylindrical system of coordinate. But looking at this equation, we have the m, which is just in a constant value of m. Okay, just a constant value of m, which is 10. And if you base on this equation, all of this, or we have, let's say, mz, yeah? dmz over the dphi. So this is all related to the differentiation of z component of m related to the p, related to the r, and related to the towards the phi and towards the r. So basically, we can see that the results of differentiation will be zero. It will be zero because your mz is just a constant value. So from here, we can see that there should be no results. There should be no results. Or I can see that the result of curl of m for this particular case of m vector will be zero. As such, we can see that there should be no generated bound magnetization current in your structure. Yeah, okay. The second one, you need to find the GSM at r equals to a. Yeah. So from the equations of GSM, in which we have learned that GSM equals to m vector cross product with the n in the vector. We have m of 10 of z cross product with the n in the vector, which is, if based on this problem, is to find the GSM at r equals to a. So r equals to a basically is on the surface of your cylinder, in which for this particular case, we can say that, we can say that the r in a vector for that particular surface will be equals to r. I mean the normal in the vector, normal in the vector related to that particular surface of r equals to a will be equals to r. And for that, we can going to see that normal in the vector will be equals to r direction. And for this, you're going to have 10 in a phi direction in ampere per meter unit. So that should be your GSM. That will be produced, or that is said to be recorded at the radius of r equals to a. Okay, so that's how we calculate both the GM and GSM related to the given magnetization vector m for these particular problems of cylindrical structure. Yeah. Okay. Let's have a look at example number 2 then. Okay, we are given a long bar of magnetic material is found parallel to the y-axis with its cross-section defined by x from 0 to 0.1, z from 0 to 0.2, and given that m equals to 3x in the y direction. The first one is to find the Gm within the material, B is to find the GSM on the four surfaces, and C is to find the total bound current that flows through a cross-section of the bar at z equals to 0.1 plane for a length of 1 meter in the y direction. Okay, so let's have a look at these particular problems. We are given a long bar of magnetic material is formed parallel to the y-axis with its cross-section defined by x and z as given here. So let's draw the structure then. So if we can sketch it to be look like this. Sorry, I need to use a red. Okay. So we are given this is your z. This should be the x, and that should be your y. Given that your structure is parallel to the y-axis, in which the x and z are given to be in the given range. Okay, so let us sketch the structure carefully. Okay, so x is from 0 to 0.1, this is 0.1, and this is 0.2. You need to use other color then, it's not that clear using the green color. Okay, so that should be the structure, which is given to be in a bar structure. Okay. Right, so that should be the structure of your long magnetic bar. Yeah. All right, which is having a x range from 0 to 0.1 and z range from 0 to 0.2, in which the bar is said to be parallel to the y-axis as shown in the diagram here. And then given that the m vector is 3x in the y direction, so then we can say that the m vector, which is the magnetization vector in the structure, is m of 3x in the y direction. That should be the given m magnetization vector. So the first one is to find the Gm within the material. So again, we need to find what should be the bound current in your structure, which is to be based on the curl of the m vector. And knowing that this is related to the Cartesian system of coordinate, so we can write that the curl of m in Cartesian can be written as dmz over dy minus dmy dz in the x direction, plus we have dmx, yeah, dz minus dmz dx in the y direction, and finally we have dmy dx minus dmx dy in the z direction. And knowing that the m is only in the y component, so we can see that there should be no mz, there should be no mx, there should be no mx, there should be no mz. Okay, yeah. Okay, and the rest we're going to have differentiation of m related to z. There should be no z variable, so the my over dz will give us 0. Okay, we'll give us 0 then straight away. And the my over dx, then we're going to have 3. Yeah, so we're going to have a 3 in the direction of z. Okay, so the my over dx will give us 3 then. Yeah, so gm is equals to 3 of z. Yeah, so that should be your volume, I mean the bound magnetization current density, the gm, which is in the units of ampere per meter squared. Yeah, because this is a volume current, okay, in your structure. Okay, and then we have to find the JSM on the 4 surfaces. Okay, so for the JSM, basically, since we have 4 surfaces related to the bar, we have surface number 1 at the top, surface number 2 at the side, surface number 3 at the bottom, and surface number 4 at the other side. Okay, so we need to find the JSM for this particular 4 surfaces. So for my case, I'm going to give an example of one surface only, which is on the top surface, surface number 1. So for surface number 1, sorry, for surface number 1, yeah, we're going to have that the JSM, yeah, surface number 1, the JSM will be equals to m cross n. Yeah, m cross n. So we have m, which is 3x in the direction of y, cross product with the n. N for the first surface, the normal unit vector will be in the z direction. So for that, we're going to have n will be equals to z direction. And for this, we're going to have 3x. So y cross z will give us x in the vector. So that should be the JSM related to the first surface on the top, which is in the units of ampere per meter. Yeah, so the same things applied for the other 3 surfaces, surface number 2, surface number 3, and surface number 4. So you only need to know what should be the normal unit vector related for the rest of these 3 surfaces. Yeah, right. And for the part C, yeah, the third question is to find the total bound current that flows through a cross section of the bar at z equals to 0.1 plane for a length of 1 meter in the y direction. So need to find out what should be the total bound current that flows through a cross section of the bar at z equals to 0.1 plane, yeah, 0.1 plane for a length of 1 meter in the y direction. Okay, so we have a cross section of the bar at z equal to 0.1 plane. So we can see that for 0.1 plane, that should be this particular surface. Yeah, that should be the surface. Yeah, the surface, the plane of z equal to 0.1. Yeah, this is z equals to 0.1. So that should be the surface. And we need to find out what should be the amount of total bound current that flows through a cross section of the bar at z equal to 0.1 plane for a length of 1 meter in the y direction. Okay. So for this, we need to use the JM terms then, the JM terms here, because we are dealing with the bound current inside the structure. So for that, we can say that to find the current, yeah, we are given the JM. Yeah, we are given the JM. We obtained the JM earlier, which is 3 in the direction of Z. Okay, so for this, we can find out the current, the total bound current should be written as I equals to integration of J dot ds. We need to use this equation, yeah, because this is the equation that relates the volume current J and the total current of I. And in this particular case, our J is the Jm. So we're going to use the J to be equals to Jm, which is 3 in direction of Z. And the ds here need to be based on the ds of this particular plane of Z equal to 0.1. So I can sketch that my ds will be on this particular surface. So that should be my ds. And my ds should be equals to dx and dy in the direction of z, which is similar to the direction similar to the j unit vector. Yeah, so we can have the ds to be dx and dy in the direction of z. So from here we can then find the current. So I will be equals to 3 integration of dx and integrations of dy. Okay, in which the x will be having a range from 0 to 0.1, because the plane here at z equal to 0.1, the plane, the x will be having a range from 0 to 0.1. Yeah, that should be the range of the x. While for the y, that should be based on the questions in which given here that need to find the current for a cross section of the bar for a length of 1 meter in the y direction. It means that the y is having a length of 1 meter. Okay, so from here we can find out that the current produced or the current that is said to flow on the cross section of the bar at z equal to 0.1 will be equals to this resultant integration, in which it will be equals to 0.3 ampere of current. Okay, so that should be the current, the total bound current that flows through a cross section of the bar at z equals to 0.1. Yeah. Okay, I hope it's clear on the solution for example 1 and 2. Basically, these examples are used to show the methods, the techniques on calculation of bound current, both Jm and JSM, related to the magnetization vector. Okay, and we're now going to proceed with the third objective, which is to see the effect of magnetization on the magnetic field in your magnetic material. Okay, so for this, we need to go back to the basic equation of Maxwell. We have seen this in lecture 16. Yeah, this is related to the Ampere's law, the equation in which the point form of the Maxwells is given by curl of H equals to J. So this is basically obtained from the Ampere's law. Yeah? Right, so in a free space condition, we can write that the H will be equal to B over mu naught. So that should be in the free space condition. So we have curl of B vector over mu naught is equal to the J, right? So basically what we're going to see now is that we have magnetic material, yeah. Okay, we have applied field, yeah, applied field to this particular material, let's say H. So we're going to see what should be the effect on the flux density B inside your material here. Yeah, so that's what we're going to see in your magnetic material. If we apply the external field of H to it, what should be the resultant flux density that will be produced in your magnetic material? So this will be our discussion basically. So for this, as I mentioned, we have to start with this Maxwell's equation. The curl of H equals to J in a free space condition. So when we consider this equation in your material, we can then say that your current density in the magnetic material will consist or will need to include the volume current Jm, yeah, in which the Jm, which has been discussed earlier, is due to magnetization. Okay, so instead of just having J in your magnetic material, we can also have the volume magnetization current, the Jm, which is a produced current in your material as a result of magnetization effect. So now the equations become like this, where the curl of B over mu naught will be equals to the summation of J vector plus the Jm. And we have learned before that the Jm is written to be the curl of M vector, the curl of the magnetization vector. And as such, we can say that these terms of curl of M can be brought to the left-hand side. Yeah, can be brought to the left-hand side. And as such, we're going to have this condition whereby the curl will be now consist of these terms, whereby we have B over mu naught minus the M vector, and that will be equals to J. And what we have to do now is that we're going to compare this with the basic equation of Maxwell that we have used earlier, where we have the curl of H, equals to J. Sorry for this. So we have, this is the case, yeah, we compare this equation with the curl of H equals to J, the earlier used equation. And from here, we can, when we compare these two equations, we can see that the H basically will be equals to B over mu naught minus the M. And when we rearrange this equation, it will become like this, whereby we have the B will be equals to mu naught of H plus of M. So basically, this should be the case whereby in your magnetic material, okay, earlier we have the external field applied to the material. So in this particular structure or in this particular magnetic material, due to the generated magnetization vector M, we can record that the flux density B inside this material will be equals to the mu naught of H plus the vector of M. So that should be the flux density or the magnetic flux density that will be generated in your magnetic material as a result of the magnetization vector. Yeah, so generated M will be contributed to the flux density in the magnetic material. Okay, and the relationship between the M and H is given by this equation, whereby M is equals to the kappa M of H, whereby the kappa is known to be the magnetic susceptibility of the material. Okay, and from here we can then write that this equation will be equals to mu naught mu r H. Yeah, mu naught mu r of H, in which if we write it carefully, you're going to have that B equals to mu naught of H plus mu naught of M. Okay, and we can write that should be mu naught of H plus mu naught kappa M of H, and that will be equals to mu naught 1 plus kappa M of H. Okay, and these particular terms is equals to this final equation, whereby we can see that mu R is equals to 1 plus kappa of M. And this mu R is what we call as magnetic permeability of the material. Yeah, magnetic permeability of the material. And this mu R is unitless. Yeah, this mu R is unitless. Okay, and if we base on this relationship, it is depending on the magnetic susceptibility. Yeah, so we can see clearly here that the mu R is related to the kappa of M by the equations of equation of mu R equals to 1 plus kappa of M. So end up, we can see that previously in a free space environment, we have B equals to mu naught of H. This is for the free space environment. But for a magnetic material, we can now write that the B should be then equals to mu naught multiplied with the mu R multiplied with the H. So in magnetic material, we have to multiply the mu naught of H with another parameter which is known to be a magnetic permeability of that material. Okay, so this is the effect of magnetization to the magnetic field in your material. Right. So then we're going to say that the mu R, yeah, the mu R will be actually used to determine the type of magnetic material. And as we have mentioned here that this mu R basically will be depending on the characteristic of the dipole moment, because we have seen previously that the M vector, the magnetization vector, will be depending on your dipole moment. Yeah, will depending on dipole moment. And we have then see that the kappa or the amp, yeah, relationship with the H, with the field that intensity H is given by M equals to the kappa M of H. Yeah, and from here we have seen that the mu R is depending on the kappa from the equation of 1 plus kappa of M, in which you can see that the mu R will be depending on kappa, and kappa will be depending on the M, and the M is depending on the dipole moment. So end up we can see that the mu R, yeah, the mu R value, yeah, the mu R value, which is the magnetic permeability, relative magnetic permeability, will be depending on the dipole moment. Yeah, mu R is depending on your dipole moment of M. Yeah, so that's why I mentioned here that the characteristic of dipole moment will be used to determine the magnetization and subsequently the mu R. So we have seen here the change, the different, yeah, the effect of the dipole moments towards the M vector, which is the magnetization vector, and subsequently on the effect towards the magnetic permeability of mu R. Yeah. Okay, and for this we can see that the type of magnetic material shall be based on the values of mu R, and these are the typical materials of the typical classification of magnetic material. We have the first one is called as a diamagnetic, yeah, diamagnetic, in which the value of mu R will be smaller than 1. And the use of this diamagnetic material is normally used in high-speed train, in which is used in magnetic levitation. Okay, that should be the application of diamagnetic. And then we have the second type is called as paramagnetic, in which for this paramagnetic material, the mu R value would be higher than 1. Yeah, and the applications of paramagnetic normally used in the magnetic stripe on the back of your credit card. Yeah, so that should be the common application of paramagnetic material. And then we have the ferromagnetic, which is very common, ferromagnetic, in which the value of mu R for this type of material will be very, very much higher than 1. Yeah, and this is normally used. Yeah, the application of ferromagnetic is normally used in your motors, your generators, and in your transformers, whereby the needs to produce a very high value of magnetic flux, yeah, shall be then applied in these particular applications. So that's why we have the case of ferromagnetic, whereby the mu R is much, much bigger than 1, so that a very huge value of flux intensity, yeah, will be produced, and that will be then applied in this type of application, the motors, generators, and transformers. Yeah, so these are the common materials, a common classification of materials, which will depending, yeah, which are depending on the values of your relative magnetic permeability, the mu R.